All right, let's dive right into this explainer. Today we're taking a pretty wild ride from the massive, literally earth-shattering scale of planetary science all the way down to, well, your very own living room. Earthquakes are easily one of the most awe-inspiring and devastating forces of nature out there, but the story of how humanity has actually learned to understand and survive them, it's just as incredible.
It's a totally terrifying thought, right? The ground we completely trust to be solid, suddenly vibrating and rolling like a liquid. But to truly wrap our heads around how we survive that, we've got to look at the whole picture. We need to explore how scientists track these massive planetary waves, how brilliant engineers practically work miracles to fight them, and ultimately, how you can prep for them at home.
And honestly, this brilliantly captures just how long we've been battling this exact problem. We're talking about a brutal building code from the Babylonian Empire dating all the way back to 1750 BC. It shows the timeless, life-or-death stakes of humanity's struggle against nature's raw power. Building codes have existed for centuries purely to keep us safe when the Earth decides to move.
So, let's start at the macro level. The science, tracking Earth's seismic waves.
When an earthquake hits, it unleashes invisible seismic energy that shoots outward. The first ones out of the gate are P waves, or primary waves. Think of them kind of like sound waves. They compress and stretch the rock, zipping along at incredibly fast speeds, up to 6 kilometers per second. But then come the S waves, the secondary waves. They travel at about half that speed. But here's the kicker. They shake the rock sideways. And it's that violent lateral, side-to-side movement that actually wreaks most of the havoc on our buildings.
Now, capturing these waves used to be a real headache. For decades, we relied on analog seismographs, using physical pendulums. The huge flaw there? During a major quake, the electronics and those old analog phone lines had a super limited dynamic range, meaning they'd easily just go completely off scale. It was a mess. But today, we've leveled up to the global seismographic network. We're talking about roughly 150 permanent, digitally connected stations all over the globe, packing 24-bit digitizers right at the sensing site. This means we can capture everything from the tiniest little tremor to an absolute monster quake, perfectly on scale. It essentially gives us a flawless, digital heartbeat of the Earth.
All right, let's scale things down. Meso. The engineering, evolution of building codes. How does human innovation try to actually tame this force at the city level? Let's trace the history in California, since it's basically been the world's testing ground for this stuff. This timeline reveals a bloody but entirely necessary progression. The 1906 San Francisco quake sparked the very first real discussions. But it actually took the 1933 Long Beach earthquake, which absolutely wrecked 75% of the city's public schools, to trigger the Field Act, which finally mandated strict standards. Jump forward, and the 1971 San Fernando quake caused multiple hospitals to collapse, forcing the creation of the Alquist Hospital Safety Act. It's a tough reality, but literally every major earthquake has forced engineers back to the drawing board to radically update regulations to protect the public.
Through all of this, there was a massive aha moment. By the late 1960s, engineers realized that structures don't just need to be strong, they desperately need something called ductility. See, if a building is just stiff and rigid, it exhibits brittle failure. It just cracks and completely collapses. Ductility is the flexibility to actually bend and distort without snapping. Think of it like a dry twig versus a fresh green branch. The twig snaps right under pressure, but the green branch, it just naturally bends.
Which brings us to another meso-level topic, the engineering, the steel frame flaw.
This part is a genuinely wild engineering mystery that caught the whole industry completely off guard in the 1990s. We're looking at a standard detailing for welded steel moment frames. This specific beam column connection was the absolute gold standard used between 1970 and 1994, explicitly prescribed by the Uniform Building Code. Everyone, and I mean everyone, thought it was incredibly safe and ductile. But then came the 1994 Northridge quake. And well, it proved them all wrong. Following that earthquake, inspectors discovered that tons of these exact connections had suffered severe, brittle fractures right at the welded joints. No bending, just snapping. That single catastrophic flaw forced a massive pivot across the entire engineering world. It triggered a wave of rigorous new guidelines for evaluating and fixing existing welded steel buildings. Suddenly, universities, hospitals, and property owners had to aggressively retrofit their structures. A really brilliant example of this is Stanford University's Mitchell Earth Sciences building. Built in the 60s, it totally lacked this modern ductility detailing. So to fix it, instead of tearing it down, engineers cleverly added exterior shear walls. It essentially slapped a whole new earthquake-resisting system onto the outside of the building without even disrupting the people working inside. A perfect showcase of the modern pivot to true ductility.
Okay, time to get to the micro level. The individual, your earthquake safety plan.
We've scaled down from planetary seismic waves to steel beams, and now we are zooming right into your own living room. Seriously, look around your home right now. Are you actually prepared? Spotting hazards before the shaking starts is absolutely your first line of defense. Think of it as a physical challenge. You need to actively fasten heavy shelves securely to your walls and put the heaviest stuff on the bottom. Grab a ladder and brace those overhead light fixtures so they don't come crashing down. Secure your water heater. Strap it directly to the wall studs and bolt it to the floor. And hey, if you've got deep plaster cracks in your ceilings or foundations, get them repaired, because they could be red flags for hidden structural defects.
All right, let's say you've done all that prep, but suddenly the earthquake actually hits. You need to bypass your immediate panic instinct and execute 3 rapid-fire steps. 1. Drop to the ground. Do it before the earthquake throws you down. 2. Take cover under a really sturdy piece of furniture, like a heavy desk or table. 3. Hold on tight until the shaking completely stops. And if you're stuck somewhere without a desk nearby, just crouch in an inside corner of the building and cover your head and face with your arms.
Now, your strategy totally changes depending on where you happen to be. If you're indoors, stay indoors. Research consistently shows most injuries happen when people try to scramble around inside or run out the door. Just avoid glass, windows, and outside doors. But if you are outdoors when it hits, stay outside. Move into an open area, as far away from buildings, trees, and utility wires as you can. To put this into a bit of dark perspective, during the 1933 Long Beach earthquake, a lot of the 120 fatalities actually happened because people ran outside of buildings only to be crushed by falling exterior debris. Believe it or not, ground movement rarely kills people. Falling objects do. Okay, the immediate shaking stops. Deep breath. But your job isn't done yet. You have to anticipate aftershocks. These are secondary waves that can hit hours, days, or, no joke, even months later. And they can absolutely bring down structures that were weakened by the main quake. You need to immediately inspect your home's utilities. Look for frayed electrical wires or damaged water lines, and this is absolutely crucial. If you smell gas, do not light a match, do not even flip a light switch. Just open a window, get out of the building, and turn off the main valve outside. Once you're safe, grab a battery-operated radio to listen for emergency updates.
And that brings us to the end of our explainer. I want to leave you with this final, really vital thought. Scientists have built these incredible global digital networks to track the very heartbeat of the Earth. And structural engineers, they spent well over a century redesigning our entire cities with incredible ductility just to protect you. But your ultimate survival? That literally comes down to your own readiness in those few crucial seconds. We can engineer our buildings to survive the Earth's worst, but have you engineered your own preparation? Thanks for joining me to explore this, and please stay safe out there.